Here you. So long story short, there exist invertible bases, all right? And I mean, it actually would be an interesting project to really prove that carefully and methodically. It definitely would.
A little star by
I mean, if you get interested in it and you find a better proof of it, feel free to show me later. But like I do think that some kind of induction proof there's probably. I should stop talking about it. I really don't have anything to add to that. Now, but since we did start talking about the norm just a little bit, so I want to talk more about examples in the time we have left, but I did want to mention that let's see here, my theorem 5.1.
Skip it around.
Yeah, just jump ahead here for a second.
Okay.
So my theorem 5.1, in a nutshell, says if you got an n-dimensional associative algebra over the reals, then there exists a norm for A, and there exists so. So there exists a norm, and M sub A, an element of, the reals, such that, in fact, M sub A positive, all right? The norm of x times y is less than or equal to M sub A times the norm of x, norm of y. And I give a formula for M sub A. In fact, I state that theorem 5.1 stated a little bit differently. I say then there exists a norm such that this, where M sub A is equal to a particular thing. M sub A is equal to the max ofCijk. Well, excuse me. M sub A is equal to M sub A is equal to n squared minus n plus 1 times the square root of n. Times big C, where big C is the maximum of the absolute value of the structure constants. And here, this is all done with respect to that ad hoc norm I was defining down here, actually. So that's the norm. I say, okay, given that, basically the theorem, I'll just give you a thumbnail sketch of the theorem. The theorem basically says, okay, so given the algebra, you pick a basis, so you can expand the elements of the algebra with respect to the basis.
Yeah.
You define the norm by this rule down here. All right. So that gives you the norm, the existence of the norm, and then I just calculate. Essentially, I just look at x times y is equal to the sum over I, j, and k, 1 to n, of c, I, j, k, x sub I, y sub j, and then the basis, v sub k. And then I just, take the norm, I probably square it because that's easier. And then I just stone cold do a calculation using index notation. And that's on page, it's equation 40 in the paper. I don't want to write it out. Do you see it there?
Yeah.
And so through some, somewhat relatively straightforward calculations, I work my way to, n times n squared minus n
Yeah.
plus 1 squared times c squared, norm x squared, norm y squared. Take the square root of all that, you got the relation, right? So what this proves is that any n-dimensional associative algebra can be given a norm with respect to a given basis, which makes the norm submultiplicative. So this, this right here, this kind of interrelation between the product and the norm, I call this submultiplicative. I don't think I spelled that right. Submultiplicative. Okay. Now, how does that relate to, say, the complex numbers? So here's an example that's really not an example of this so much as it is something else. So for complex numbers, right? The norm of a complex number, I usually just write modulus of the complex number. If it's the modulus of x plus iy, well, that's the square root of x squared plus y squared, right? And of course, it's also...
No. Wouldn't it be minus y?
No, complex numbers.
We're talking about the difference,
Right, so this is...
the length between 2 points?
Yeah, I mean, this is the distance from the origin out to z, or the length of the vector z, depending on how you measure it.
Okay, I thought you were okay. But yeah.
And you're probably thinking about this discussion we had, I think, ZZ bar.
Yeah.
That is the square root of ZZ bar. So the product of the complex number its conjugate gives you the norm squared. Great. And so yeah, the norm of ZW in the complex case is the square root of ZW times ZW conjugate, which by the way is ZZ conjugate, WW conjugate, and you can square root, and there you go, norm Z, norm W. So, in fact, this is what's called a multiplicative norm. Right. It's not submultiplicative, it's multiplicative, because you don't have a less than or equal to, you just have straight equality of I mean, essentially it's an example of what's boxed in green up here, right? It's just m sub a is equal to 1. And that's true for all x and y, right? So complex numbers with their standard norm, the norm is in fact multiplicative.
So complex numbers follow the norm of the reals, essentially?
Well, if we just look at the complex numbers as R2.
Yeah.
Yeah.
Okay.
Right. Now, I should warn that, caution, and I've seen research papers be confused about this. The norm in H, right? Z bar, x plus jy, times x minus jy, equals x squared minus y squared. Right, that's what you were thinking about
Yeah.
a minute ago. That's not a norm.
Why? Oh, it could be, no, but it's squared. No, but it could still be a I value, right?
Well, it could be negative.
Yeah.
But worse yet, if this is the norm, right, then, I mean, we can even throw in an absolute value just to be magnanimous, all right? This is sometimes done in special relativity. They'll take the absolute value of the difference of squares of things where the difference could be negative. But if this was the definition of norm here, what's the norm of 1 plus j?
1,
1 squared minus 1 squared. Because x is 1 and y is 1 here.
Oh, yeah. 0.
Is this 0? That's not 0.
No.
They have the norm of something non-zero is 0. That flies in the face of the fundamental definition of norm. You can't have the norm of a non-zero thing and be
Yeah.
0. That's not normal. Sorry, that's horrible. But it is nevertheless the fact that this function here, although it's not a norm, it is a multiplicative function. In the sense of whatever you want to call this thing, if we call this, we could call this thing like, instead of calling it norm of z, we could call it Bob of z, And you could prove that Bob of zw was equal to Bob z times Bob w. It is a multiplicative function, but it's not a norm. It does have its purposes, and much can be gleaned from the Bob function, as is if you read literature on hyperbolic calculus. It's just not something I'm terribly invested in at the moment, because it's not something that's general. I'll just tell you, as you study associative algebras in more generality, it's just not the case that there's a Bob function. There does not exist Bob in a general algebra. Like, you can't find a multiplicative function that's interesting, as far as I know, for arbitrary algebras. And it's because this simple story of conjugation, like there's a z and there's a z bar, such that the product of z and z bar just gives you back, well, maybe I'm wrong. Maybe there are multiple Bob functions. I could be wrong about that. I should think more about that. Maybe there are many Bobs. What I'll explain to you as we go on here is that for an arbitrary algebra, because this is this is like the first thing that Min started this whole mess in like summer 2012, and Min become obsessed with generalizing conjugation.
Is he a student or someone else?
He's now a PhD student in math at Arkansas.
Oh, okay.
He's interested in like hard questions of differential geometry. It's somewhere in between analysis and he's more in the direction of analysis at this point. Like all deep geometry at some point becomes like analytical PDE stuff. So don't it's like, oh, I'm going to be in differential geometry. I'm not interested in analysis. It's like it's not a reasonable perspective. Like it all goes together. And only the simplistic level of differential geometry doesn't seem to involve analysis. That's just because I'm focusing on the linear algebra. If it doesn't seem like it's analytical, that's just me. That's just your instructor. Anyway,
analytical in what sense, can I ask?
Convergence, divergence, continuity.
Oh, okay.
What's open? What's the correct class of functions to look at?
Yeah.
What's the theory of integration? Can you extend local functions to global functions? Questions like this.
Oh, okay.
Does there exist a non-vanishing vector field? Space, stuff like that. So we was very interested in the question of like, for a three-dimensional algebra, can you find a conjugate such that like z conjugate gives you back a real quantity, and such that real and such that that bar obeys the usual laws of conjugation, like z1 plus z2 bar is z bar 1 plus z bar 2, and zw bar is z bar w bar, right, like that. And I don't think you can. Not in general anyway. And I guess there's a couple different directions to go with what you mean by a generalized conjugate. There's something called Galois theory. There's a notion of conjugation in Galois theory, which has to do with like the totality of what's called the Galois group. So like in Galois theory, the conjugates are the automorphisms of the Galois group. So those are like one-to-one onto mappings that send generators to generators. And, it turns out that Galois group is essentially just like Z2. It's the group of order 2. So you've got the identity and you've got one conjugate. That's what happens for complex numbers.
Well, that makes sense, yeah.
So like so when we is that the right way to say it? Anyway, I will just, without getting into a course of Galois theory, I'll just say there's a notion of conjugation in Galois theory that can be studied. There's this pretty much separate notion of conjugation that I develop in this paper. That's a modification of the author I mentioned to you, Ofelia Lopez Gonzalez. He and a few other authors I should remember the names of, they developed a conjugation for an n-dimensional algebra. And I looked at what they did and I thought, first of all, I was like, this is amazing because this is what I was trying to do, and I couldn't see past my concept of just having one conjugate. They understood that they didn't need just one conjugate, they needed many. So they didn't define one conjugate for an n-dimensional algebra. They defined n minus 1 conjugates for an n-dimensional algebra. So it just happens in 2 dimensions, there's just one conjugate.
But n minus 1.
Yeah, but in 3 dimensions you have 2 conjugates. And they also didn't care. I mean, this was less apparent to me at the start of this investigation, but it's true. They didn't care that their conjugate of a product is not the product of the conjugates. You don't have multiplicativity of their conjugates. And I don't know. I don't even think that it's I don't even think it's the case that the product of the algebra variable and the conjugate of the algebra variable is a real quantity. I don't think that's even the case. I have to look at that though, now that I think about it. I don't think that's the case though. We'll see for sure in about 10 minutes. So they developed multiple conjugates, and the purpose of their conjugates and mine, because what I did was I took their notion of conjugation and I changed it ever so slightly to what I think is the correct definition. And in my quote-unquote correct definition, I find a very, very elegant statement of the Cauchy-Riemann equations over an algebra using my conjugates. In complex analysis, I rattled this off and went into the solutions to your differential geometry stuff,
Yeah.
but I didn't really explain it. But I mentioned that you can state the Cauchy-Riemann equations as this for C.
Why is that?
Why is that?
Yeah.
Well, so the question is, what does partial z bar mean? All right, I'm going to show you some formal nonsense. So this should be something like partial x, partial z bar, partial x plus partial y, partial z bar, partial y. Again, this is formal nonsense. Because, I mean,
This is the conjugate, right?
well, z is what? It's x plus iy. Z bar is x minus iy. So this gives me x is equal to 1/2 z plus z bar, yeah. And y is equal to...
Well, you don't have the z term, so everything... Yeah.
y is what? It's 1/2i.
Yeah.
Z minus z bar. So on the basis of this formula and that formula, what do you think partial x partial z should be?
first we do x, so that would be
What's partial x partial z bar, given that this is the formula for x in terms of z and z bar?
there's chain rule it.
So you can assume that partial z bar is 0.
Yeah.
If that's the case, partial z bar is 1. So we should just get like a half for that.
Yeah.
All right. What's partial y partial z bar? There's no 2 up here, that's a 1. Idiot.
1 over 2i.
Almost, but notice there's a minus over here, right?
Oh yeah.
So
Minus
1 over 2i, right?
yeah.
Now we can rewrite that as 1 half
Partial y.
partial x plus I partial y.
Which doesn't. How does that work out?
Well, exactly. How does that work out? So f equals to u plus iv, right?
Mm-hmm.
So let's try partial z bar on f. What do we get? 1 half partial x plus I partial y u plus iv. How does that work out? What does that give us? You got yourself a ux.
Yeah.
I times I is minus 1 minus
uy.
minus v.
Oh yeah, vy.
Vy, right? Plus I over 2. Uy.
Yeah. We've done this. We were doing this, but it was a little different.
Uy plus
Vx.
Vx. So this is what partial f partial z bar is. What happens if you impose the Cauchy-Riemann equations? What are the Cauchy-Riemann equations?
Partial f over x2 equals partial, no. That's,
In terms of u and v,
was that the uxx?
nope.
Is it the u plus jb is equal to minus x plus c1j?
It was, I mean, I just wrote them down. I mean, there is ux equals to vy,
Oh yeah, vx equals to uy.
minus uy.
Yeah. Okay. Oh wait, it's minus uy?
Yeah.
That's when you do the partial u partial x of u squared plus b squared, and the partial v of partial x of 2uv.
I think that was when I was talking about Laplace equations rather, but this should have been one of the first things I said. I mean,
no, I have that somewhere.
you can get it from matching up the regular representation.
I found it.
You found it? Okay.
This is the j of uv a is uy with equal to bx, b is by equal to u.
Now, if there's a j there might not be this minus because that would be the hyperbolic number example.
Yeah. Yeah, that's the only difference. We did the hyperbolic. I don't think we did the complex.
Well, I did work out that the regular representation of the complex looks like a minus b a.
Yeah.
And then I compare that. So if u plus iv is a complex differentiable function, that means that its Jacobian matrix must be in the regular representation of the algebra.
Yep.
And the Jacobian matrix is this, right?
With the little line in the middle, right?
So, yeah, I mean, I didn't draw the lines, but so these have to be equal, right? And if the matrices I just wrote in blue up here are equal, what does that tell you? I mean, that tells you this.
Yeah,
right
uy
here.
is equal to bx, but it's minus.
So, getting back to my conjugate calculation down here, what does that tell us? I mean, ux equal to vy.
Ux equal to vy. Oh, that's 0, and that's 0.
And that's 0, right? So, in other words, imposing the Cauchy-Riemann equations gives us that that's 0, but in fact, this is a general identity. Once you once you, you know, define what you mean by partial z bar. So, I mean, what I'm trying to tell you is this right here is actually a definition. It's not a, that wasn't actually a chain rule. And the reason that that's not actually a chain rule is because, well, you're switching from a function of a complex variable to a function of a real variable. So at best, you're giving a notation for the derivative with respect to another real variable. It's more of a definition than it is a derivation, actually. So, but anyway, the larger point here is you make that definition, you calculate this partial derivative, and you can see that it being 0 is true if and only if what? If and only if the Cauchy-Riemann equations hold. So, given a real differentiable function, Cauchy-Riemann equation, in other words, one for which the partial derivatives exist, the real partial derivatives exist, it's satisfying complex Cauchy-Riemann equations if and only if the derivative with respect to the conjugate variable vanishes. So this is well known to like students of complex variables who've gotten far enough into it. It's possible to teach a complex variables course where this doesn't get discussed, but it's, you know, pretty low level stuff. And through a similar calculation, actually partial z is 1/2 partial x minus I partial y. And if you calculate the product of partial z with partial z bar, what happens is you get a 4th partial x squared plus partial y squared. And so this is why Min was always interested in this question, is he wanted to know, this is the Laplacian. So Min, from his very early days, has been fascinated by the Laplacian and how to factor the Laplacian. He's still studying that question now, in a very different regard. So this is why we became obsessed with this question. It's like, how do you factor the Laplacian for other algebras? So it's like a 3-dimensional algebra, the Laplacian would have been like x squared, partial x squared plus partial y squared plus partial z squared. And how would you factor it there? Yeah. So that was a motivation for this whole, you know, inquiry to start with. And I've never actually answered those questions. We just went other directions and found all kinds of interesting results. In fact, I've come to decide that I've actually come to sort of partial non-answers that I think can't be overcome. But anyway. So, before I forget, in terms of future things we should learn. This submultiplicative norm, this was later, another question that it becomes is like, what's the best choice of m sub a? Right? This m sub a I've just defined in terms of taking the maximum of the structure constants in absolute value. But if you look at the calculation that led to in the proof of this theorem, you'll quickly realize it's very heavy-handed, the calculation. I'm making some very gross overestimates. And so it stands to reason for a particular algebra, maybe you could improve that. I think when you do that calculation for the hyperbolic numbers, let's see here, hyperbolic numbers, n is 2. So you get like 4 minus 1. So that's 4. And then 4 times square root of 2. And the maximum structure constant in the standard basis is just 1. So I think we get 4 times square root of 2 if I didn't make this calculation. So, you know, that's what it is. But it turns out, if you study the hyperbolic numbers carefully, you can prove that the best constant that you could put there is the square root of 2 itself. So 4 is a greedy overestimate of what needs to be there. So King studied this more carefully, and King defined the submultiplicative constant to be the best constant that you could put there. The best constant that you can put there, it'll be such that for certain quantities, certain elements in the algebra, that inequality becomes sharp. It actually becomes equal. And so he actually derived, he actually found, calculated this sharp, the best submultiplicative constants for a wide class of algebras in a paper we published. And he, in that paper, essentially, he has a proof that it's the square root of 2 for the ordinary hyperbolic numbers. And he has a proof that it's the square root of n for the n hyperbolic numbers, if I recall correctly. And he also calculates it for some other examples. But that's a difficult paper in my view. I'm just saying that there is further nuance that can be added here, but it's not super important to our starting point, because really we just need to know that we can write that kind of inequality for the norm. That'll become important as we study limits and actually trying to prove that certain limits exist, and how you tame certain things, like this is useful, the existence of that constant. But yeah, Kane came back after it was like Christmas break. He's like, I think I solved your, or it may have been summer break, I forget. But he's like, I think I solved the question you asked. I'm like, what? And then he started showing me stuff. I'm like, what? And then I rewrote what he did, and he made me a co-author, and that was I don't know, I did a lot of work for that project, right? But the actual hardest part of it was his. There's something really neat in what he did in terms of the relation. It actually is somewhat closely tied to understanding how different examples are isomorphic. Because this norm stuff, it becomes the most trivial to understand when you have the direct product algebras. The formulas are most simple to understand. So if you can build an isomorphism from your example to the direct product algebras, and then you can have that isomorphism also has nice properties with respect to the norm, then that's enough to prove, to calculate things through that isomorphism. That's essentially what he did in this paper. But, and then he has harder, horrible things, remember the nilpotent algebra order 3 I showed you at the end of last time, that 3x3 thing?
Yeah.
He calculated some multiplicative norm for those. He has the full proof for n equals to 2, and then he claims results for n equals 4 and 5 that are just, they're probably correct, but we don't have proofs written down because they're just so horrible. I digress. Okay, so examples, right? So I just wanted to give you a quick view of that, just at least say a little bit about the norm, because as we're studying calculus, we do need to discuss the limits, and the limits are defined in terms of the norm. So things we know about the norm for a general algebra are valuable to us. But I think it's good for us to invest more time in a particular example.
What's a norm for the reals? We'll just do the distance equations.
Yeah, norm for reals is just absolute value.
Mm-hmm.
So, because in the absolute value b minus a is the distance from a to b.
Yeah.
It's just more the same.
That's interesting that the hyperbolics are like that. No, but then you said in differential geometry that you're talking about a specific thing.
Yeah, we got that. We didn't worry about any kind of algebra structure there, Yeah. There's no product, it's just geometry. And, there's a direction, if we could come up with an interesting question that relates to something in differential geometry, to the algebra that we're looking at here, like if there's something to investigate there, that of course would be an interesting project. So if you think of something, even if it's just in a fuzzy sense, tell me. Sometimes students have had fuzzy ideas that I've been able to make real papers. Like it happens. Because when people are first learning it, you have all kinds of ideas that I don't have.
Yeah.
That's one of the great, I think, undersold values of having undergraduates do research is you bring fresh ideas, perspectives. And I'm not saying that in a sit in a circle of chairs and sing Kumbaya English kind of way. I mean, like real perspective, not. Okay, I'll stop saying things now.
Yeah. I was interested in that one question of the quadratic equation in a general sense, in an abstract sense that you have. I was interested in that.
Yeah.
But I only think you could do that with, I think you'd have to assign an equivalence class to algebras for a generic
I think
quadratic formula.
I think solving the quadratic equation for a given algebra is a difficult question.
Yeah.
Solving the quadratic equation for a wide class of algebras all at the same time makes me nervous. I mean, maybe you could do it, I don't know, but okay, so let's look at an example. I'll say it's the reals plus JR plus J squared I. In other words, what I'm saying here is A plus BJ CJ squared, such that A, B, C are real, and J cubed is equal to 1. So, you know the cyclic group of order 3?
As in, I gotta think for a second. I wish I had a notebook with me. I'm gonna say no for now. I'd probably do if you like ran it by me.
Well, it's got 3 elements in it. It has the identity and the generator.
Yeah.
And so like, sometimes some books will call it C3. Something like E alpha squared. But I would point out you could make it 1 J squared and then J cubed equal to 1. This
C3, is that like? No.
It's a group of order 3
Yeah.
that is defined multiplicatively. So you just take products of one. I mean, I can make the Cayley table for it. Do you want me to?
No, it would just be 1 times J is J, 1 times J squared, J times J squared is 1. No. Yeah, it's 1. And then J squared is J.
Exactly. So J and J squared are inverses, and 1 is its own inverse.
Yeah.
That's a cyclic group of order 3. There is something in abstract algebra called the group algebra. So this is something that you can take any group, say like G1, G2, let's say N, a nth order group, and you could define, and man, I forget the notation, but I'm just going to say group algebra. I'm going to say the real group algebra of G. And that's just going to be G1, G, direct sum, G2, O reals, not G. And the way this works is if you have, like a sum I equals 1 to n of a sub I, g sub I, and you multiply it by a sum, j equals 1 to n of b sub I, b sub j, g sub j, that's just equal to the sum over I and j of ai, bj, and then gi, gj.
So you take a sum of the j terms, and then you take a sum of the, okay. Yeah.
That's the real group algebra. So in other words, what the real group algebra does is it takes a nth order finite group and it associates with it a n-dimensional real vector space where the multiplication of the group is built into the basis of the vector space. And the basis of the vector space stands, it is literally taken to be the elements of the group. But you got to understand, it's the elements of the group
That can be generated.
that are thought of linearly independently.
Yeah, but in 3 it would just be the 3. And they all
Okay.
linear.
I'm just saying, you got to be careful, because an example of this would be the group, which is the number 1 and the number -1, right? And if you were to build the real group algebra from this, okay, you should think of it something like v1 equals to 1, v2 equals to -1, and elements in the real group algebra of G, or whatever, I don't know notations, but whatever that is, it's going to be things like AV1 plus BV2, such as A and B are real, right? And you're tempted to write that as A minus B, but you can't. Because in this real group algebra construction, you're constructing a vector space where the basis of that vector space is formed from the group elements. So if your model of the group, whatever it is, has built into it a linear dependence amongst the group elements, that must be forgotten in the construction of the real group algebra. Otherwise, bad things happen because it's not the real group algebra. This notation is meant to be external direct sum, which means you're taking these to be independent subspaces. This worry I have is not going to be an issue for us unless we happen to have a group that we're forming the group algebra from, where the elements of the group have linear dependence amongst them.
So we're saying our elements in our group have linear dependence because they're scalars of each other? Because one and -1 are scalars.
Yeah, this one. Right, yes.
Okay. I was just like, why can't you write it like that? I was like, why? What are you saying? But if we have like 1 and 0.
Well, I'm just saying, if you did, well, I mean, you could write it as A times 1, plus B times -1, but what you can't do is ever transfer things from here to here. These have to be thought of as linearly independent.
Oh, okay.
It'll get you into trouble. I've gotten very confused over this issue in certain examples over the years. Still the only reason I mentioned it. Yeah. Now, this J squared, what's a model for the cyclic group of order 3? What could you use?
A line?
A line?
Because you can invert it, rotate it 90 degrees. No, that would just be a rectangle.
See, like, you could use the units of order 3. You could, like, use e to the 2 pi I over 3.
No.
You could let that be j. Because you have 1, you have j squared. So if this is j and this is j squared, j times j squared gives us j cubed over here, which is equal to 1, right? So if that was your model, if that was how the group was presented for you, and you were to form the group algebra, you must not. You are forbidden from making use of the relation that j plus j squared plus j plus 1 is equal to what?
E? No. E, 2e 2 pi I?
E to the 2 pi I, yes, what is that? Oh, no, not e to the 2 pi I,
No, that'd be 6 pi I?
no. Look at, I mean...
No, it's 1, I'm sorry.
No. What is the sum of, let me make it, let me be a little bit more heavy-handed in my hinting. What is the sum of
2 pi?
this vector,
Uh-huh.
this vector, and that vector? Because this vector is 1,
3?
that vector is j, that vector is j squared, not 3, no.
J. Are we saying like when we do the table, it would be j?
No, I'm asking, what is the sum of j plus j squared plus 1? Maybe.
What is the sum of j plus j squared plus 1? Give me a second.
What's the sum of 1 and minus 1?
0.
Mm-hmm. This is the units of order 2. Order 4, a group of units, roots of unity, order 4, 1, I, minus 1, and minus I. That's e to the 2 pi I over 4, which is, by the way, equal to I.
No, you're saying that's equal to like...
So yeah, what's the sum of these? 1 plus I plus minus 1 plus minus 1.
That'd be 0?
It's 0, right? Yeah.
But that wouldn't be 0, it'd be 1.
No, it's 0.
Because you're going around once?
No, because this has one real component.
Mm-hmm.
That's minus a half over. That's minus a half over. So minus half gives us minus 1.
Oh, I see. Okay.
So the horizontal parts of that cancels with that. The vertical part of this one cancels with the vertical part of that one. We get 0. But like, this is true. This is true not even for roots of unity, but for like, if you take the nth roots of any complex number and you sum them, they have to sum to 0 because the nth roots of a complex number appear symmetrically around the origin. So if you think about averaging, think about it as a center of mass calculation.
Mm-hmm.
Like the center of mass of those n roots is always the origin.
Okay.
So, but my point, this is a very long point to make for, all I'm trying to say here is, I really, it doesn't quite do these justice to think of them, the j squared, to think of them as e to the 2 pi I over 3. Because e to the 2 pi I over 3 is, after all, a complex number. And if you have 3 complex numbers in the 2-dimensional complex plane, there is a linear dependence amongst them. Here it is. But I am not imposing that linear dependence amongst this one j and j squared forming this algebra, right? So that's something to keep in mind as I present examples. When I say, you know, this algebra has a unit j such that j cubed is 1, I'm also assuming that 1, j, and j squared are linearly independent elements of the algebra. So,
Can you do that?
yeah,
Okay.
I can. Let me show you. Can I erase?
Yeah.
Sure. I'll give you a second. I have some Gatorade in here. I'm going to find it. Ah, I knew it. for best results, I have to drink a couple swallows of Gatorade and then put it away. Because if I keep drinking it, I find like I'm just like at the end of drinking a whole thing, I'm just like, oh, why did I drink a whole thing of Gatorade? It's very like, I'm not running miles and miles of track with you,
Sorry.
or sprinting. Let's see here. Okay, so you've asked the question of existence. How do I know that there exists such a, such an algebra? How could I build it? Right?
Yeah.
There are various ways.
And are all algebras constructed in the form of like an a plus variable b?
Oh, no. You can have algebras that require more than one generator.
Okay.
Certainly, yeah. Yeah. So one very efficient way to build algebras is, like here, I'll show you one. Let A be real polynomials in X modulo the ideal generated by x squared plus 1. So this is from some abstract algebra too, but so this is a quotient ring. It has the following form basically. It's a plus bx plus the ideal generated by x squared plus 1. But the rule in this quotient ring, all right, is that f of x plus the ideal generated by x squared plus 1 is equal to g of x plus the ideal generated by x squared plus 1. The words I'm saying very fast are ideal generated by x squared plus 1. So this is equal to this, I'm defining, by the way, definition. If and only if f of x minus g of x is an element of x squared plus 1. Now you might say, what is this? You never even defined what that means. Fair enough, you caught me. So this is a of x times x squared plus 1 such that a of x is a polynomial in x. So this r with a bracket, that's just polynomials in x, okay? That's okay?
This is r sub bracket?
This is polynomials
Okay.
in x. That's okay, right?
Yeah. So when we're doing generators, we did like very simple ones, just like how x to the first can generate all the other x to the n power stuff. If I remember right.
With me or
With Rakovich.
I'm not sure what you guys have done.
That's what I remember doing. We were doing like all the generators of x to a power.
Oh, okay, so yeah, that's a different kind of generator.
Okay.
Not disconnected, but here we're talking about generation through product of polynomials.
Yeah, well, what I see here is that we generate it by multiplying anything by that x squared plus 1. So x squared plus 1 is divisible by everything. Or everything in this group would be divisible by x squared plus 1.
Yeah, it is a product of,
Yeah.
I mean, a sort of a snazzier notation for this might be,
Yeah.
multiples.
Yeah.
Okay, so first of all, since this has the number 1 in it, right?
Mm-hmm.
That means that x squared plus 1 is in here.
Yeah.
So check this out. X squared plus 1 is equal to 0. Excuse me, I've already violated the rules of the game. X squared plus 1 plus this thing, which is getting really annoying to write, is equal to 0 plus this thing, which is getting really annoying to write.
No, plus the order?
No, that's 0. Why is that true?
No, not 0. I'm talking about the brackets.
That's just the ideal generated by x squared plus 1.
Okay.
You could call it I if you prefer, but maybe let's not do that. We call it big J or something. Whatever. Okay. So
No, that's fine.
So the point is, if you drop this notation, this equation becomes x squared plus 1 equals 0.
Well, 0 is divisible by x squared plus 1. If you had a function that was 0, that would just straight line across 0, it's divisible by x squared plus 1. Right?
I don't know about that. Excuse me. Let's see here. So, kind of beg the question of everything at the start up here. I said that things in here can be written as a plus bx plus that. All right, but from like base principles, if you have the real polynomials modulo some ideal, then what that is f of x plus I such that, you know, f of x is a real polynomial. So a question you could have asked me to start with was, how do I know I can just write a plus bx here? Now you didn't ask that question because, again, this is from a course you haven't taken. My apologies.
Okay.
But why could I reduce this f of x from an arbitrary polynomial to just this? Well, the reason I could do that is because in the ideal, in these objects, I can just I can replace x squareds with -1. So like, if I have a plus bx plus cx squared plus dx cubed plus the ideal, in the ideal, I can trade x squareds for -1. I can trade x cubes for -x. So this just becomes a minus c plus b minus e times x plus the ideal generated by x squared plus 1. Because again, I have this relation up here which I can use.
Oh, okay.
The representative in this quotient space is not unique, just like fractions are not unique. Fractions in the original quotient space. Of course, 1/2 is 3/6. Same kind of thing here. These, equivalence classes, in fact, they have many representatives, and you can manipulate the representative by this relation we just found, that x squared plus 1 is equal to 0, or you could equivalently derive x squared is equal to -1. All right? And so it turns out you can apply that over and over and over again, and additively and multiplicatively, and the whole shebang, and you get this. So without loss of generality, an arbitrary element, this goes on, right? If it had a higher order, you can always collapse all the even ones into the constant and all the odd ones into the x. And so you can always just collapse it down to a plus bx.
That's the same way we collapse constants just to 1c, even if we integrate more than one time.
Right, so if you have a plus bx plus the ideal, all right, which I'm just going to call big J for now, and then c plus dx plus j times the ideal, the way you multiply in the quotient space, the polynomial quotient space, is you multiply representative.